Some more compounds for the discussion of structure followed by the oxidation states. The first one is chromium pentoxide, CrO5. Chromium is having 3d4s electronic configuration, that is 6th B group. Maximum it can shows +6 as the oxidation state. But as for the number of oxygens are concerned, it is showing +10 as the oxidation state, which is abnormal. Abnormality is present in such a way that some of the oxygens are involved in peroxy bond. Here the difference of maximum and the as per theory is concerned, the oxidation state of chromium is 4. 4 implies 4 oxidation numbers should be minimum. That is 4 oxygens are involved in peroxide bonds. That is 2 peroxides are there. 2 peroxy bonds are associated with the 4 oxygens. Thereby for each oxygen there is a decrement in oxidation number of 1 unit. Hence the structure related to the chromium pentoxide is like this. Chromium pentoxide. This is chromium pentoxide structure. The next one is persulfuric acid H2SO5. Whereas as per the hydrogens and the oxygens are concerned, here we are expecting the oxidation number of +8 for the sulfur, which is abnormal. The maximum can be shown by the sulfur is of 6. So therefore here also abnormality is present in peroxide bond. So therefore in the form of peroxide bond it is present. H2SO5. Here one peroxide bond is there. Due to this peroxide bond, for each oxygen, oxidation number is decreased by 1 unit. Hence the maximum oxidation state shown by the sulfur is of +6. And peroxide disulfuric acid, it is also in the same fashion. This is peroxide disulfuric acid. One peroxy bond is there and 2 sulfuric acid units are connected. And now ammonium nitrate, the structure of ammonium nitrate is ammonium in the form of cation, nitrate in the form of anion. Ammonium nitrate, oxidation number of, here the nitrogen is of -3, every hydrogen is of +1, and here nitrogen is showing +5 and every oxygen is showing -2. The last one is sodium borohydride. Borohydride, boron can combine with the 3 hydrogens and it is having vacant orbital. This vacant orbital, if it is allowed to combine with the H-, overall it will becomes BH4-. This BH4- is counterly balanced by sodium cation is said to be the sodium borohydride. Hence sodium shows the +1, whereas boron shows here one of the boron is sodium borohydride. So therefore boron is less electronic to compare it to the hydrogen. Hence what we can feel is every hydrogen is of -1, boron is +3 and sodium is of +1. Stock notation. When oxidation number of metal is written in Roman numericals in parentheses of the representation of formula, then that particular representation is known as stack representation. Otherwise the notation is known as stack notation. Suppose ferrous sulfate is there, potassium dichromate is there, manganese oxide Mn2O7 is there, manganese oxide Mn2O7 is there, and chromium oxide Cr2O3 is there. Whereas the corresponding oxidation numbers of metals in ferrous sulfate is iron is of +2, potassium dichromate is chromium is of +6, and Mn2O7 manganese is of +7, and chromium of Cr2O3 is of +3. So while representing FeSO4 with Fe followed by 2 in the Roman numericals. Similarly in K2Cr2O7 chromium followed by 6 Roman numericals. Mn2O7 Mn with the Roman numericals of +7 and Cr2O3 of chromium +3 Roman numerical is written in the parenthesis. Such kind of this representation is known as stock notation. Cyanide, that is some of the ions, ligands, formulas followed by the corresponding charge present on the species. Cyanide Cn- structure is carbon followed by the nitrogen with triple bond, whereas both are having lone pairs. Carbon is having 1 unit of negative charge, overall charge is -1. Nitro NO2-, whereas it is derivative of nitrous acid. So therefore here hydrogen is removed in the form of H plus, oxygen is holding 1 unit of negative charge. So therefore that is oxygen is having total 8 electrons. Out of these 1, 2, 3, 4, 5, 6. Here another one lone pair is present, that is nitro NO2 with 1 unit of negative charge. Hydroxo OH from water, H plus is eliminated, and thiocyanate. Here S is connected with the cyanide, and here cation is removed from the sulfur and it is having 3 lone pairs, S minus. Sulfide ion, sulfur with the 4 lone pairs, that is S minus 2. Sulfato from sulfuric acid derivative, carbonato from carbonic acid, carbonic acid derivative, ammonia everybody knows. Nitrosyl neutral is there, and also thiocarbonyl similar to carbon monoxide. No atom is having charge, hence it is neutral overall. Triphenyl phosphine, phosphorus is connected with the 3 phenyl rings and having lone pair without having any charge. Nitronium NO2 plus, similar to that of this particular nitro NO2 minus. This is nitronium NO2 plus. More electronegative species left from the oxygen by taking the lone pair, hence it is having NO2 with 1 unit of positive charge is said to be the nitronium ion. Halide ion, X minus, halogen with the 4 lone pairs having 1 unit of negative charge. Nitrate ion NO3, which is a derivative of nitric acid, NO3 minus, whereas one oxygen is holding 1 extra electron, that is 1 unit of negative charge. Overall it is having 1 unit of negative charge. Amide from ammonia, if 1 hydrogen is removed, then NH2 minus is said to be the amide, whereas it is having 2 lone pairs. Here originally it is having 1 lone pair, now extra 1 lone pair is present. Acetate, CH3COO minus, oxygen is having 3 lone pairs, and here it is, generally it is having 2, now extra it is having another 1. So therefore this is acetate ion, 1 unit of negative charge. Sulfate ion, that is sulfur with the 3 oxygens, one is double bonded oxygen, remaining 2 are single bonded oxygens having each 1 unit of negative charge, that is sulfite minus 2 units. Similarly thiosulfate H2O3 2 minus, oxygen is having minus 1 unit on each, so therefore it is totally 2 units of negative charge. Similarly amide, imide is nitrogen of the ammonia. If 2 hydrogens are eliminated, then that will be NH of minus 2, that is said to be the imide. Aqua water, carbonyl CO and phosphine pH3 similar to ammonia. Nitrosonium, already we made the discussion that 1 unpaired electron is removed from the system, it is having a lone pair followed by a double bond with the oxygen having 1 unit of less electron, that is nitrogen with positive charge is said to be the nitrosonium cation. Formal charge. For the charge, the responsible fundamental particle is electron. If more electrons are there, it is having negative charge. If less electrons are there, then it is having positive charge. Sufficient number of electrons are there, it is neutral, it does not have any kind of charge. So formal charge, that is charge associated with the atom in chemical combination, is known as formal charge. So formal charge is count of number of electrons difference. How many are there, how many are to be there. The difference between them decides the formal charge. For each 1 extra electron, we will say it is having 1 unit of negative charge. For each lack of 1 electron, we will say it is having 1 unit of positive charge. For sufficient number of electrons, we say 0 formal charge, hence it is neutral. Definition can be given like this. Formal charge is charge assigned on the atom of an element in a molecule, assuming that electrons in all chemical bonds are shared equally between atoms regardless of electronegativity. So till now in the calculation of the oxidation number, we are taking electronegativity as the reference. Total pair is shifted towards one of the atom. But now in the calculation of this particular formal charge, regardless of this electron negativity, we have to consider that electron is equally shared between the atoms. Then we have to count how many are there, how many are to be there. Difference will decide the formal charge present on the atom of an element in the chemical combination. Formal charge will becomes equal to group number of atom involved in chemical combination minus of twice of lone pair of electrons plus 1 time of bond pair of electrons. It can also becomes equal to number of valence electrons minus of twice of number of lone pairs plus 1 time of number of bond pairs. Yes, calculation of formal charge for the atoms of elements present in the water molecule as well as the ammonia molecule. Water H2O, the structure of water is oxygen connected with the two hydrogens. Now hydrogen is connected with oxygen single bond, oxygen connected with the hydrogens with the two single bonds having two lone pairs. Now formal charge of hydrogen can be given by group number of hydrogen is 1 minus of number of lone pairs present on hydrogen 0, twice of 0, and number of bond pairs, only one bond is there, bond pairs are 1, so therefore that is 1 into 1. So therefore this will becomes equal to 1 minus of 1, that will becomes equal to 0. There is no formal charge. We are expecting 1, we have 1, hence there is no extra electron, hence the charge present on the hydrogen in water molecule is 0. Similarly, let us go for formal charge of oxygen in water molecule. Yes, group number is 6 minus, how many lone pairs are there? 2 lone pairs, twice of lone pairs, 2 into 2. How many bond pairs are there? 2 bond pairs, 1 into 2. Total will becomes equal to 6 minus of 4 plus 2, that is 6 minus 6 is equal to 0. Similarly, in case of ammonia, formal charge of nitrogen can be given by 5, group number minus, here how many lone pairs are there? 1 lone pair, and the bond pairs are 3, 1 into 3, total 5 minus 5 is equal to 0. Similarly, in case of hydrogen of ammonia, 1 minus 1 will becomes equal to 0. Hence the formal charge of all the atoms of elements in water and ammonia are 0, total molecule is also neutral. Let us go for the extension of the formal charges. Suppose water molecule is dissociated in the form of H and OH minus. Then what are the formal charges present on the H and OH? Now let us count. Here we are expecting 1 electron in the hydrogen as far as the valency is concerned. That is formal charge of hydrogen. Group number is 1. Whereas here minus of lone pairs are 0, bond pairs are 0. Hence the formal charge is plus 1 on this hydrogen. Let us go for this oxygen which is generated from the water molecule. This is formal charge of oxygen can be given by, what is oxygen's group number? 6. 6 minus of, how many lone pairs are there? 3 lone pairs are. This bond pair is shifted as a lone pair towards the oxygen. Hence 3 into 2 plus 1 into, how many bond pairs are there? 1 bond pair is there. Total, this is 6 minus 7 is equal to minus 1. Hence minus 1 is the formal charge present on the oxygen of the hydroxide. Similarly, ammonia already we made the calculation, nitrogen is 0, hydrogen is 0. Suppose if it is present in the form of H plus, already we made the calculation, NH2 minus. Let us have a look for this nitrogen of this particular one. Group number is 5 minus number of lone pairs, 2 into 2 plus bond pairs, 1 into 2. Total will becomes equal to 5 minus 6 is equal to what? Minus 1 is the charge. Whereas now once again it is converted as H plus followed by N with 3 lone pairs and the hydrogen. Now we have to calculate the formal charge on this nitrogen. On this nitrogen, that will becomes equal to 5 minus number of lone pairs 3 plus number of bond pairs 1. That is 5 minus 6 plus 1, that is minus 2 is the formal charge. Similarly, if suppose this is dissociated as hydrogen followed by the nitrogen, once again nitrogen with the 4 lone pairs, we are expecting 5 electrons, we are having 8 electrons, hence the formal charge on this nitrogen is minus 3. Thus formal charges are generally calculated. Formal charge on the ozone. Ozone is O3, oxygen molecule plus another one oxygen atom combination is O3. O2 we know, O2 when connected with the oxygen, then here O3 formation takes place. In this case what happens is one of the lone pair present on the oxygen atom is donated towards the vacant orbital present on the oxygen atom, hence it leads to the formation of such kind of electron readjustment is there. Now let us calculate the formal charge. Formal charge of this oxygen, whereas group number 6 minus, here 2 lone pairs are there, 2 into 2 4 plus bond pairs are 2, hence it becomes equal to 0. Whereas formal charge of this oxygen is group number 6 minus lone pairs, that is 5 of lone pair, 1 lone pair, bond pairs are 3. So therefore this is plus 1, hence the formal charge is +1 for this oxygen, whereas for this oxygen group number 6 minus, number of lone pairs are 3 into 2 6, plus bond pairs 1, that is 6 minus 7 is equal to -1. This is the formal charges, those are present over the oxygen, hence it is said to be the dipolar ion. You remember one thing, that monovalent cation, divalent cation, trivalent cations. Cation implies what? Less by monovalent, less by 1, divalent less by 2, trivalent less by 3. Hence the charge present on that is +1, +2, +3. Similarly, anions, monovalent, divalent, trivalent are excess by 1, 2, 3 electrons respectively, and corresponding charges are -1, -2 as well as -3. Valency, it is the combining capacity, it is always non-zero and it is a whole number, and it depends on the number of valency electrons. It is always whole number because atom always combines in a simple whole number ratio with the other atoms. Due to this reason, it always a non-zero whole number. Valency can also be defined with respect to the number of monovalent and the divalent and trivalent atoms combined with a reference atom. That is, the number of monovalent atoms combined with an atom of an element is known as its valency. Suppose in case of methane, carbon is combined with 4 hydrogens, every hydrogen is monovalent, hence the valency of carbon is 4. Whereas in case of chloroform, here carbon is combined with monovalent atoms of two varieties. That is, one is chlorine, 3 chlorines are there, and second one is hydrogen. All are monovalent. With respect to this chlorine monovalent, it is 3. With respect to this hydrogen, it is 1. Total it is 3 plus 1 is equal to 4. Whereas with respect to the divalent, double to the number of divalent is said to be its valency. Oxygen is divalent, both oxygens are divalent. Whereas here carbon is combined with the 2 divalent atoms. So therefore 2 into 2 it becomes equal to 4. This is monovalent as well as the divalent combination. Carbon combined with 2 monovalent atoms and 1 divalent atom. So therefore here monovalent 2 and divalent 1 is of 2 plus 2 is equal to 4. Whereas the number of trivalent atoms with which atom is combined is also known as its corresponding triple to the number of trivalent atoms combined with an atom of an element is known as its corresponding valency. Whereas in case of hydrogen cyanide, carbon is combined with here trivalent atom nitrogen and monovalent atom hydrogen, hence the total valency of the carbon is 4. Maximum covalency, the maximum number of covalent bonds, otherwise maximum number of bonds formed by the atom of an element is said to be its corresponding maximum covalency. Suppose in case of oxygen, oxygen will form 2 sigma bonds, covalent valency is 2, whereas the lone pair present on the oxygen can be donated towards the vacant orbital containing similar sized atom like protonium, hence it can form H3O plus, in that the maximum covalency of oxygen is 3. Whereas nitrogen normally forms 3 bonds, whereas on donation of lone pair present on it towards the similar size containing cationic species like protonium, it forms ammonium ion, the maximum covalence will become equal to 4. Similarly, phosphorus maximum forms 5 bonds, whereas in presence of F minus, it can also acting as an electron pair acceptor with the another fluorine atom, it can form PF6 minus, and here the oxidation maximum covalence of the phosphorus is 6. Carbon always forms only 4, whereas xenon generally forms 6 as the coordination valency, whereas under extreme cases it can form 7 also, but a higher value compared to 7, that is xenon tetroxide. Xenon is having 8 as the oxidation valency, 8 bonds are formed by the xenon, hence the maximum covalency of xenon is 8. Calculate the formal charges on each of nitrogen present in the azide, each of atom present in the carbonate, that is CO3 2 minus, sulfonate of SO4 2 minus, nitrate of NO3 minus, nitrite of NO2 minus, and the potassium ferrocyanide K4FeCN6. that is each atom of azide, carbonate, sulfate, sulfite also. Sulfite to nitrate, nitrite, as well as potassium ferrocyanide.